name is Zachary Dickinson. I'll be presenting undergraduate work done by Newton Karra under Dr. Wayne Strasser. This will be on the influence of EGR on performance and emissions in a combustion ignition engine fueled by Jatropha biodiesel blends. So a quick introduction. Uh, this will just be an experimental study on the performance, combustion, and emissions done using Jatropha biodiesel blends. Biodiesel can be produced from a process called transesterification that we'll talk about in a second. And that's by taking certain vegetable oil esters, then converting them into usable fuel. We'll also be talking about exhaust gas recirculation and its effect on engine performance parameters, brake-specific fuel consumption. We'll talk about that in a second, as well as exhaust emissions, which is a big part of this talk. So some of the advantages of biofuels. Sorry, I just realized I had my clicker. Uh, some of the advantages of biofuels. A huge one is that they're sustainable. Instead, there's large concern about running out of the world's oil reserves, but there's also concern on the environmental issues. Biodiesel most of the time is sulfur free and protects catalytic systems. Very little engine modification needed, and can be blended with diesel, which is really good for our infrastructure instead of just like switching all the way to electric or the like. We can slowly input it into our infrastructure. Can also improve engine life via lubricity. So why does this matter? Well, diesel plays a huge role in the transportation, industrial, and agricultural industry. On average for 2026, there will be around 30 million barrels a day. Largely, that's for transport. And again, biodiesel, it can work in most diesel engines, most conventional diesel engines with minimal changes. And as transport and our infrastructure builds, so does our need for diesel. We also have emissions that, that's a large concern of our society, and we're trying to mitigate the environmental aspects. So some of our engine parameters, as I said, this was an experimental study. We use a single cylinder 4-stroke constant speed direct injection diesel engine, tested using 100% pure diesel, 15% Jatropha biodiesel, 85% pure diesel, as well as a 30% Jatropha and 70% diesel blend at 50% and 100% loads. This was at 220 and 240 bar injection pressure with a constant timing of 23 degrees before top dead center. So quick thing on 23 degrees before top dead center. Not all of us might be diesel mechanics, but this is actually really interesting. So as you can see, I would use my laser, but it doesn't work. As you can see here, we have the piston in the cylinder, and so before top dead center is it's the fuel injection timing. So as the piston is moving up the cylinder, when it reaches this 23 degrees, I know that says 10, but just assume it says 23. When it reaches 23 degrees, that's when the fuel gets pushed into the cylinder, the valve opens up, and the fuel is pushed in. And then at top dead center, it combusts and then transitions into the next thermodynamic cycle. There we go. So, process of biodiesel. How do we get biodiesel from Jatropha? This is a really interesting and honestly pretty simple process. We take so Jatropha is a type of tree native to South America. And so the process is pretty simple. We take the seeds of this Jatropha tree, we crush them up, we push them together under high pressure, and from there we get this oil. and through a process called transesterification, we convert that into conventional biodiesel. So what is transesterification? Transesterification converts oils or fats into biodiesel by breaking apart the triglycerides within the oil. This is caused by mixing them with alcohol, whether that's methanol or ethanol, as also with a catalyst, potassium hydroxide or sodium hydroxide. So as I said, triglycerides are break apart. That forms glycerol as well as biodiesel, and then some further refining is done to um, to make them usable for engines. This is an apparatus of what my colleague used. As you can see, you have a hot plate stir right there, and then that's the mixture of Jatropha oil, I believe methanol and potassium hydroxide. This reaction is exothermic, so it'll be heated up just enough for the reaction to start to occur, and then heat will be taken off and it'll just be mixed. So EGR, this is also a big point of this presentation. Exhaust gas recirculation. It's really fascinating, actually. So exhaust gas recirculation takes the exhaust gas out of an engine and it recirculates it back to the air intake of the engine. What this does is it raises the temperature of the air intake and lowers the oxygen, uh, lowers the amount of oxygen in the air intake. This reduces nitrogen oxide emissions. Uh, this needs to be done with sensors, uh, because too much of it will reduce efficiency and it is not good for the engine. However, we can see that EGR reduces nitrogen oxide emissions. So keep that in mind as we walk into this next part. This is just a picture. Oh, sorry. Next slide. I'm sorry about that. Again, our experimental test rig, single cylinder, 4-stroke water-cooled diesel engine. An eddy current dynamometer was attached to it. We had sensors, we controlled airflow, we controlled all these things, computerized it, made it so that we can actually have a viable experiment. Here's a picture of our experimental setup as well as our smoke meter. Here's some of the experimental analysis results obtained. Again, this was done at 220 and 240 bar injection pressure, injection timing of 23 degrees before top dead center, 50% and 100% engine load. Engine load just refers to the amount that the engine can actually, the amount of power the engine can actually produce. So 100%, that's the max amount that it can produce. 50%, half of that. And then just these are fuel codes. You'll see D100, JB15, D85. This just refers to what the blend is that we're using. Brake specific fuel consumption, really important. It is the ratio of mass flow rate, the fuel mass flow rate to brake power output. This is fascinating because this measures efficiency of engines regardless of whether they're 4-cylinder, 8-cylinder, a V setup, a straight setup. It measures independent of volume as well, because it just measures the mass flow rate of fuel into the engine as well as the power output. So the lower the BSFC, brake specific fuel consumption, the better the fuel efficiency. All right, some of our results and conclusions. Here you'll see our brake specific fuel consumption at 220 bar and 240 bar at 50 and 100% loads. The blue is D100. Then we have 15% Jatropha biodiesel and 30% Jatropha biodiesel. So as you can see, the brake-specific fuel consumption raises just a little bit, and this is an indicator of the performance actually decreasing. Sorry, the efficiency. Sorry, I'm losing my voice. But just keep that in mind. It reduces efficiency just a little bit, but here's where it's interesting. This is carbon monoxide versus load. Again, 220, 240 bar. And these are some of the different blends. And as you can see, the carbon monoxide actually lowers as we introduce Jatropha into the fuel. And this really just shows that this is viable for reducing emissions. This is very, very interesting concept. There we go. Next up, we have the rate of pressure rise versus crank angle. So if you ever heard a diesel engine from 5 blocks away, and you're like, wow, that is loud. That is because it has a very high rate of pressure rise, ROPR, as some call it. The higher rate of pressure rise, the louder an engine is, funny enough. But here we just see, this is just a graph of how, sorry, the Jatropha one is on the next, this is 100% pure diesel. Here we have the Jatropha, the Jatropha biodiesel. And it says JTME, that's just Jatropha methyl esters, which is essentially your biodiesel. And what these graphs show us is that there's an actual ignition delay with the introduction of Jatropha biodiesel, which is causing that reduction in brake-specific fuel efficiency. How that works is actually really fascinating. So as we talked before about before top dead center and the ejection timing, at top dead center is when the combustion process happens. So reaches top dead center, boom, and then it switches its to the next part of the thermodynamic cycle. With a shorter ignition delay, that's meaning that it is igniting before it reaches top dead center. This can cause strain on the engine, but also lowers the efficiency, which is why we say minimal modifications needed, because likely the before top dead center, when we're injecting the fuel into the engine, that would likely have to change in order to see some differences in our efficiencies. So that's just some of the future work that hopefully will be done. No promises, but I would love to see that work done in the future. So some of our conclusions, we see that biodiesel blends show shorter ignition delay, lower rate of pressure rise. The brake thermal efficiency is slightly decreased because brake-specific fuel consumption is increased, and this is at 23 degrees before top dead center. If it was at a different fuel injection timing, we could see some different results. So we see that also the introduction of Jatropha biodiesel significantly reduces hydrocarbons and carbon monoxide emissions. And at identical EGR levels, biodiesel do produce higher nitrogen oxide emissions, but by increasing our EGR, again, our exhaust gas recirculation, we reduce nitrogen oxide emissions. And just excessive EGR will reduce our performance, but with the right amount, we believe that Jatropha can provide a sustainable and transformative adjustion to our fuel sources for the infrastructure, agricultural, industrial, and transportation industry as far as their diesel engines. And 15% was found to be the best trade-off. But anyways, thank you very much for listening. Please let me know if you have any questions. Yes, Crash.
So you're increasing your fuel consumption just a little bit, right? And you're adding the Jatropha to get the same output.
Well, it's a result. The brake-specific fuel consumption is a ratio of our intake mass flow rate for our fuel over the amount of energy produced. So as the amount of Jatropha, dude, I'm sorry, my voice is just cracking today. But as the amount of Jatropha in our fuel increased, the brake-specific fuel consumption decreased, which shows that our brake-specific fuel consumption increased, which shows there is a decrease in our efficiency. Does that make sense?
Yeah.
Okay.
So if you're producing X power per cycle with a given mass, 100% diesel, and say 15% Jatropha, 5% diesel, and you have I think your emissions rate slide said that you were decreasing somewhere in the order of 0.2% of carbon dioxide emissions or monoxide emissions. How much carbon monoxide are you actually saving per unit energy that you have to expend? If that makes sense.
Basically. So if I'm getting your question right, could you restate that? That was interesting.
So you are decreasing your carbon monoxide emissions by, in this case, the 100% load at 220 bars, right?
Yeah.
If you're using the 30%, 70%, so the green, you're going from about 0.25% carbon monoxide to like 0.225%.
Yeah.
So my question is, how much carbon monoxide are you really reducing per unit energy that you produce, since the drop in the percent that you produce is so small, I guess.
That is. Oh, sorry.
If you scale it
Yeah.
on a per output,
Yeah.
it may not be better.
That's my thing. That's my question.
Maybe you need so much power to run it.
That is a wonderful question. I don't have the data on me right now, but I would like to also state that the ignition delay can also be the cause of a decrease in efficiency. So I believe more studies would have to be done on different injection timings before that we can say that it's just like not as efficient. Because it is a different substance, though it's similar in its composition. It's gonna have different heating value properties, and with that, just like getting the timing right of when the fuel needs to be injected so that it does combust at top dead center. Does that make sense?
Yeah, that makes sense.
Awesome.
Actually, in reality, you want the combustion to happen differently depending on how fast the engine goes.
That's right.
And higher RPM, you want to have that even sooner. Anyway.
Yes. Yes, Thomas.
Yeah, I mean, the session is technically over now.
Okay.
But I think there's a short break right now.
Did you guys examine any fouling in the actual engine using this mixture?
That's a wonderful question. I personally did not have a hand in this project. That was a colleague of mine. I can send you his email for that question. But that's a really good question. Thomas, did you have
Mine's
one?
actually
Okay.
kind of related. Now I don't know a huge amount. I'm still learning my combustion stuff, so
Yeah.
fair warning, what I'm saying may be completely wrong. I am pretty sure that nowadays engines run a little bit fuel lean.
Mm-hmm.
So fuel lean means less fuel than the oxygen consumed in that fuel. There's extra oxygen.
Mm-hmm.
And they do that for a reason. When you do this engine recirculation thing, you're reducing the oxygen, you're making the fuel more rich. Did you look at any of the reasons as to why they run lean, and are you subverting them by doing this engine recirculating? Like, for instance, you're noticing less NOx. Well, yeah, that was one of the side effects of going lean, was we made more NOx. We went that way for a reason. I think it was because we were making soot. So
Yeah.
you make soot instead.
That's deep. I love that question because yes, I did. There's some more research just on the background, and you're 100% correct. There is what's called, I think it's the nitrogen oxide soot problem that scientists face, and it's really just this balance of like, hey, either way, we are going to produce either nitrogen oxide or soot. So where is the middle ground of where we're gonna make our engine like stand, where it produces, and that will honestly always be a problem. But yeah, that's definitely something more research could go into. Thank you. Exactly. Thank you.
All right,
Awesome.
thank you.